So the next speaker of the morning is Aarts from Swansea University again, and Gert will tell us about quantum fields and machine learning.
Yeah, let me just, I'm not going full screen because then I can't see anything. So thanks a lot, Biagio. So this is also on work with Dimitrios and Biagio, but in a slightly different direction. So just by way of introduction, although Dimitrios of course gave a very extensive introduction of some recent work. So in the last 4 years or so, there's been a lot of applications of machine learning to lattice field theory and to other areas of theoretical physics. Many things are being tried. Say it's very interesting, I think, to work on this because anything goes, so to speak. And just to advertise a recent paper that Biagio and I contributed to for the SNOMES exercise, has a whole list of references of applications of machine learning, specifically to lattice quantum field theory. So in this talk, I will be quite exploratory, so to say. So this talk concerns what we call quantum field theoretical machine learning. It's not so much about getting high precision as in the previous talk, or really nailing down critical exponents. It's more to discuss some new conceptual ideas to explore. It's in the context of scalar field theory and something called Markov random fields. So I'll introduce this and explain why these thoughts come about, and then give some examples of directions to go into. And this work is based on the reference at the bottom of the screen there. So what's the idea? So just a one-slide introduction to neural networks or deep learning from the perspective that will be useful in this talk. So we can think of a neural network as a system with many degrees of freedom, and you may call them neurons or you may not call them neurons. And these neurons live on sides of multi-layered networks here. These neurons talk with each other in the sense that they are connected via weights, what I call weights, Wij here. These are indicated by the lines here. And these are free parameters, so to speak. And there is also on-site weights called biases, which live on the sides of the neural network. Now, these weights and biases are tunable parameters, and they are adjusted in the learning phase of a neural network training. That is to say, you want to minimize some cost function or loss function, like a mean squared error, and this is called learning. And after this stage, these parameters, these weights and biases have obtained a certain value. And subsequently, then you can use this neural network to, of course, first of all, reproduce the training task. This is what the training should give you, of course, but also then to what's called to generalize, that is to make predictions for unseen data. So this is a kind of a one-slide overview of how machine learning on neural networks work. And of course, if you think about this, this may have some similarity to a lattice field theory. So on a lattice, we have many degrees of freedom associated with sides of a dimensional lattice. We call these many degrees of freedom lattice fields. These fields also talk with each other via, say, nearest neighbor couplings, in case of kinetic energy, for instance, or local couplings, or on-site couplings for potential. And we can choose these parameters. We don't train them as on the left, but we choose these parameters if we want to simulate in a certain part of parameter space. And then we try to minimize, say, well, let's say the quantum action in kind of lofty words, but we want to do, say, Monte Carlo simulation in Euclidean lattice field theory, and then use observables after obtaining those configurations. And so there is, roughly speaking, there seems to be one could relate these two ways of thinking. We have many degrees of freedom. The many degrees of freedom talk to each other via couplings, and we want to either tune these couplings or create configurations and then use this to compute certain quantities. And so superficially, you can say there are some similarities here. And so the question is whether this can be made more precise. and that will be the first part of the talk, is actually a theorem to indeed make this more precise. And then, of course, the aim is whether this insight or this result can be used to our advantage in various directions. Either we can use the insight from lattice field theory to design new type of machine learning algorithms, or of course we can use the ideas from machine learning to contribute to lattice field theory. And so that's the idea. Can we go in either direction to learn, from one for the other. So that's the idea of the talk. And so this can be made more precise now. So the idea is that we first consider a 5 to the 4th scalar field theory, and actually use a theorem, the Hammersley-Clifford theorem, to rigorously show that a 5 to the 4th theory is a Markov random field. And then Markov random fields have been used, for some time in the machine learning community already to use as machine learning working engines, so to say. And in this way, we can establish this relation between Euclidean lattice field theory and machine learning. So to discuss this theorem here, the Hammersley-Clifford theorem, I have to introduce a few simple concepts in graph theory. So a graph has vertices and edges. So there's two examples in the bottom here. This is a bipartite graph, and this is a simple square lattice. I look at the different sides here, or vertices, and identify cliques. Cliques are points which are pairwise connected, like H1 and Phi1 form a clique. And then there is a notion of a maximal clique, which means that no additional point can be included, so that it is still a clique. So for instance, if I look on the right here, Phi1 and Phi3 form a clique. If I would add Phi4, it is no longer a clique because Phi4 doesn't talk to Phi1. And in fact, in both of these examples here, the maximum clique is just a set of two vertices connected by a line. Now, why do I say this? Because then in this particular language here, you can have a probability distribution, which is a product of non-negative functions over maximal cliques. So I have a partition function in the denominator here, and this is a non-negative probability distribution. And I can write this over the entire graph by writing it as a product over these maximal cliques. If this is the case, then this probability distribution satisfies something called the local Markov property, and the fields here, or these random variables, are Markov random fields. And this is the statement of the theorem. So it's an if and only if theorem. So if you can write P as a product like this, it's a Markov random, satisfies its local Markov property, and vice versa. Now, this does not look too unsimilar to a lattice field theory. If we go to a lattice where we have a Euclidean action in the exponent and a Boltzmann weight, where the action only depends on the local term, so potential and the nearest neighbors, so the kinetics term, then actually it has exactly this form. So if I discretize a Euclidean action, I have the nearest neighbor term from discretizing the derivative term. There are local terms from the mass and the 5 to the 4 coupling, and from the additional terms from this second interaction appear here as well. And in fact, I can then write this partition function exactly in this form of the Hammersley-Clifford theorem as a product over positive exponentials, where these exponentials basically take up this form of the action here. So if I multiply this out over all cliques, I get the original partition function as written here. And so this is a proof, so to say, that 5 to the 4th theory on a square lattice is indeed a Markov random field, and which means we can now use it for machine learning tasks. Note that I've done something special here. I've introduced local couplings. So the Wij is the nearest neighbor coupling. In a normal lattice, this would be a fixed number. And in the same stage, let's call it the mass parameter and the 5 to the 4 coupling, I've introduced indices I here, so they can depend on the local position in the two-dimensional lattice. So it's a slight generalization of the original Euclidean lattice, but of course we can restrict it by taking these couplings to be constants again and not dependent on this, on the actual location on the lattice. So to see this phi to the fourth theory now as a Markov random field, I have to change my mindset a little bit. And so the phi field is a random field. So this will become the neuron field, so to say. And the parameters here, these bilocal couplings and the local couplings are not fixed from the outset like the way we would do a lattice field theory simulation, but actually we treat them as variational parameters, and collectively we'll call them theta. And so the idea is that we want to tune these couplings Wij, Ai, and Bj to optimize some machine learning tasks. Now the reason that we allow these to be inhomogeneous or local, so to have local dependencies here, is that it makes the framework richer. There's more that can be learned, and we'll demonstrate it later in the talk as well. Of course, from a Euclidean quantum field theory perspective, it's a slightly strange theory because it's a theory where the coupling constants can fluctuate from lattice side to lattice side. But this is something that has been studied. It's something that occurs in spin glasses or in quantum field theory with random couplings. So it is a known concept, but not something that we're used to in standard lattice field theory. So a quick recap here. So the variables phi define a Markov random field. These are the degrees of freedom. We have a set of parameters appearing in the action or the probability distribution, and these will be tuned. And the tuning is done in such a way that this distribution then satisfies some conditions, or in the language of machine learning, it then completes the machine learning task. Now, what tasks do we want to achieve? Well, we essentially would like this distribution P, written down here, we would like this to learn certain properties of another distribution so that we can use this probability P instead of the distribution we try to learn. Now, there are two possibilities here. Either we know the target distribution, so we call the target distribution Q. So maybe Q is known, and we want to learn a new distribution P to mimic Q by choosing the parameters. Why would you want to do this? Well, it may be that it's easier to generate new data using this machine learning distribution P rather than the original distribution Q. So it may be a way to, say, speed up simulations or have access to parameter space where you normally wouldn't have access, say. And this is something that would crop up in our applications in field theory, where we typically know the target distribution, say the QCD action, for instance. Another example is where the target distribution Q is not known, but a lot of data is available. And from this data, we would try to learn what the underlying probability distribution is. And this is something that's very common on the internet. Say, if you look at images of faces or people or whatever images you have, we do not know the probability distribution that underlies faces, but we have a lot of data available to learn what a typical face looks like. And if you then learn this distribution, you can use it to create fake images. And so this is an example here of fake faces that have been created from the original Mona Lisa, say. And this is not only true for faces, but also for paintings or music, etc., etc. So that is the opposite case. We do not know the target distribution, but we have a lot of data available. So let's start with the first example. So say we know the target distribution Q, and we want to train our machine learning distribution P by tuning the parameters in there to approximate this target distribution. Now, the standard measure to use in this context is called the Kullberg-Leibler divergence, or the KL divergence. It's given in this form here. Q is known, P is supposed to be learned. This divergence vanishes when P and Q are equal, and otherwise it's positive. And one can think of this as essentially an expectation value with respect to the distribution P here. And so what we want to do is to minimize this divergence with respect to the parameters by sampling configurations from this distribution here, and then adapting the parameters sequentially to keep minimizing this divergence. This is something that actually looks very familiar. It's essentially a variational principle. If we write these probability distributions as essentially as free energies, so we assume they're both non-negative, so we can write them as e to the minus something divided by the partition function. If you take these expressions and you substitute them into this KL divergence expression, you get an inequality here, which basically says that the free energy of the target system is bounded by the free energy of the machine learning system in this particular way. And so the right-hand side here gives an upper bound on the free energy of the target system. And moreover, the right-hand side only depends on quantities that only depends on this probability distribution P, which is the one we know and try to minimize. So the right-hand side is completely computable. We know the target distribution, so we know A, S is the machine learning action, and this is the free energy here. And in this way, we can map an arbitrary system to a 5 to the 4 scalar field theory by minimizing this distance. In practice, this works. So it's really variational principle. So this is like an ansatz with a number of parameters, and you simply minimize the variational free energy with respect to these parameters by doing a gradient descent. In terms of in machine learning, this parameter eta is called the learning rate, which tells you how quickly you change the parameters as you minimize this variational free energy. So all of this is computable, and all these expectation values here are over the probability distribution P, and so this is updated as we minimize this free energy. So let's do a few examples. So this is where we know the target action, and for the target action, we've chosen something which is like a 5 to the 4th theory, but a little bit more complicated. So there is a nearest neighbor term, as always, but there is also a next to nearest neighbor term with a coupling G4. And then there's also a complex term in the phi squared term, so there's an I times G5 here. So this is quite a complicated lattice action, and we want to mimic this action by using our machine learning action, which just has a standard 5 to the 4 term phi squared with real coefficients, and just the nearest neighbor term with no next to nearest neighbor term. Of course, the difference is that in this machine learning action, we take the couplings to be local, and so we have more expressivity. And the idea is that we can try to use this machine learning action with local couplings to mimic this more complicated lattice action with fixed couplings. And then once we have done this, we can generate configurations with our new action here and generate configurations, say, potentially in an easier way. So I have 3 examples of how this works. The first example is just a test, like test 0.1, say. Will we reproduce 5 to the 4th theory with constant couplings? So we take as the target action just the standard vanilla 5 to the 4th theory, so no G4, no G5. And of course, we want to, during the learning, observe that, say, Wij flows to the coefficient 1 here, A flows to the coefficient G2, and B flows to the coefficient G3. So this is just a test of sanity checks of say. So we initialize this machine learning action with random couplings, do the gradient descent, and then indeed these inhomogeneous couplings flow to the homogeneous values as expected. To be honest, it's a little bit difficult to see in the plot here, but the idea is that it ends up at, say, Wij, all the Wij's end up to be 1 as expected, and so on. So this is the 0th order test to satisfy. And then we can make it a bit more interesting and now include the next to nearest neighbor terms in the target action. And so here the challenge is whether the machine learning action with no next to nearest terms, but with inhomogeneous couplings, can mimic this target action with next to nearest neighbor terms. And this is shown here for the way the Kohlberg-Leiper divergence evolves in time. And you have to look at the lower line here, so this is the learning stage. Time here means learning time. Eventually, indeed, this Kohlberg-Leiper divergence goes to 0, which means that this machine learning action is mimicking the target action. Of course, this was called A3 here is the action without next to nearest neighbor terms, but also with homogeneous coupling, so no local dependence. And then, of course, you can't do it. You don't have enough expressivity, so to say, and so the K-out divergence never goes to 0 in that case. So it shows that the inhomogeneous couplings are essential to be able to mimic this action with a non-trivial next to nearest neighbor term. Once we have constructed this probability P, or this machine learning action S, we can use it for other purposes. And in particular, we can now extend into parameter space. So G4 here was the coupling of the let me flip back, of the complex term. Oh no, sorry, that is later, isn't it? Should it be G4 or G5? I thought it was G5 actually, but maybe it's G4. In any case, what we can do here is reweight in parameter space now, starting from G4 equals 1, and reweight with this new action or probabilitization P by including a corrective step e to the minus exponent of s minus a. So the reweighting can be done, of course, directly with the original action, and this is called MC. But we can also do it with the machine learning action, and this gives agreement. So this is an application of using the learned distribution rather than the original distribution. So this was the first set of problems where we know the target distribution.
Gert, sorry, just 1 second. You have 5 minutes, about 5 minutes.
Yeah, that's fine. Yeah. So this is now the reverse problem. What if we only have data, but we don't have the underlying distribution? So then we can minimize the opposite K-out divergence. And so this distribution is with respect to Q, and this Q is approximated as a series of instances, a series of data. And this is a typical problem you encounter in image analysis. So given an image or an ensemble of images, what is the distribution that would reproduce those images as a configuration in this distribution? And so this is an example of a bird. So this is a picture of a bird, pixelated picture. And we start out with a random 5⁴ theory with random couplings. And by minimizing this K-out divergence, you can tune the couplings, or the couplings are being tuned so that a picture of a bird emerges. So I think this is quite amusing because this is essentially a 5⁴ theory, but not as Higgs intended it a long time ago. Everything I said so far was in terms of just a distribution function on essentially a square lattice. So we can take this one step further and try to construct neural networks, 5⁴ neural networks, and have more than one layer. The easiest example is what's called a restricted Boltzmann machine, where you have 2 layers and the nodes only talk to each other across the layers, but not within the same layer. So this is a restricted Boltzmann machine. And so we then have a machine learning action with 2 sets of variables, H for hidden layer and phi for visible layers. And we can make this as general as we want. So there is coupling between the layers here with Wij. But there's also then a local term in the visible layer, a 5⁴ term here. And also in the hidden layer, we can have a H² and H⁴ term. This is a generalization of something that has been studied. If you put the quarter couplings to 0, you get a Gaussian restricted Boltzmann machine. If you take the hidden layer to be essentially an Ising model, Ising degree of freedom, you get a Gaussian-Bernoulli restricted Boltzmann machine. But if you keep the visible layer to be 5⁴ theory and the hidden layer to be ±1, you get a 5 to the 4 Bernoulli restricted Boltzmann machine. And that's something that hasn't been studied yet. So in this way, we can have a whole set of different cases which can be studied to see whether they are useful to be used in a machine learning task. Just one quick example here. So 64 squared visible units in which we give pictures of faces, 32 hidden units. And what is learned here are the parameters in this action, and in particular wij here are the links between the hidden and the visible layers. And if you look at these coupling constants now as a function of I for fixed j, you see that these coupling constants have learned features in this data set, namely some features of faces here. And this is how machine learning works, or deep learning works. Layer by layer, you learn certain features which are imprinted on these coupling constants. And so one can continue this and introduce more and more layers to extract more and more features from the data. Anyhow, this is my last slide. So the proposal was that can we construct machine learning algorithms from quantum field theories, since there's quite a similarity in terms of the setup and the formulation. And in principle, I discussed that systems can be mapped to 5 to the 4 scalar field theories with inhomogeneous couplings by minimizing this KL divergence. The inhomogeneous coupling is something we're not very much used to in lattice field theory, but it does appear, say, in spin glasses or by, say, averaging over the space of couplings. So this is a new way to think about it. And of course, the hope is that maybe if we combine our expertise from quantum field theory and from machine learning, whether we can develop a kind of common framework to contribute to both areas of research. Okay, thanks.
Let's thank her for the talk. Thank you very much.